Hello everyone, welcome to CodeBeyond. I'm Sai Avinash and I'm an SRE at Google Dublin. I'm All India Rank 3 at CodeChef, Master at Codeforces. I previously interned at Uber and I'm also snagged on finalist. The subjects that I take are discrete mathematics, dynamic programming, graphs, and a lot of other competitive programming topics which frequently occur in coding interviews of great tech companies. Use the code SciLife to get a 10% off on the Unacademy Plus subscription. So what are the benefits that you get? You get to interact with India's best programmers and you get to experience the interactive live classes part. Apart from that, has it ever happened to you, you're learning a topic, but you have a lot of doubts, you're searching on the internet, but you're still unable to get the right answer. But with the doubt support option, you can get your doubts resolved with India's best programmers. What more do you need as a smooth path to where you want to be? Additionally, you get to practice problems with CodeChef and you can get those doubts resolved as well. This is a quality subscription, I'm telling you. So here's the subscription model. And use the code SciLife to get a 10% off on the Unacademy Plus subscription. So there are going to be new batches on Unacademy. All of them starting on 6th July. Mahayodha. It's a 2-month master course on advanced programming topics. There's Ekalavya 2.0. It's a complete course on Java programming for beginners. It's an 8-month durated course. And then there's Brahmastra 2.0. It's an exclusive 5-month learning track for on-campus and off-campus placements. It's a 5-month durated course. So, to follow this content, please like, share, and subscribe. Do drop a like button, as it keeps us motivated. And do subscribe. It's going to help you a lot if you have a path in programming. So let's move on to what I'm going to teach today. So let me start off with the uses of binary exponentiation. The prerequisite for this topic is watching the last video. I brought what complexity is, what binary exponentiation is. I'll just give a tiny revision. It's just calculating a to the power b super quickly by calculating smaller problems. For example, you calculate 3 to the power 100. How do you do that quickly? You calculate 3 to the power 50 and just square it. Instead of 3 to the power 50 and then you're multiplying it by 3. Instead of the slow boring process, you take 3 power 50 and multiply it by itself. And recursively keep doing it. So that way you can calculate 3 to the power 100 quickly and a to the power any b, any integer b, quickly. Awesome. Now, let's see when it's actually applicable. It's not just for multiplication. It's for any associative property. Not only multiplying numbers, any associative property. For example, any associative property. So what is an associative operator? A, B is equal to A, B dot C. Meaning, the order in which you compute does not matter. If you compute A and B first, and then C, or then do it with C, whatever that thing is, that operator is, or do B and C first, and then do A into whatever that result is. If both are equal for all possible domains, for all possible elements in the domain, then you can call that operator as an associative operator. An example is addition. We saw that multiplication is an operator, 3 into 7 into 8, which is 21 into 8 is also equal to 3 into 56, right? Do this first, multiplied by this, or do this first and multiplied by this, which is this. Simple. What other operators do you know? One of them is addition. 3 plus 5 plus 10. 8 plus 10 is same as 3 plus 15. Now you're asking why don't we do binary exponentiation for addition? So what, like, why would you do that? Like, if you want to calculate 3 into 25, well, there's no need to break this up into binary. Why? Because the computer already your operating system already knows how to do multiplication quickly. Whereas we did not have that luxury for exponentiation. Like 3 power 25, the computer, like, it won't do it for you quickly. But multiplication already here, so there's no need to break this down into whatever 2 power 4 plus 2 power 2 plus 2 power 3 plus 1 2 power 0. We could technically break it down. Like, it's gonna be stupid, but it'll still give you the essence. So why not? Like, say 3 into, first we calculate 3, then we calculate 3 plus 3, then we calculate, which is basically 3 into 2, then we calculate 3 into 2 square, 3 into 2 cube, then 3 into 2 power 4. So if you want 3 power 25, 25 has these bits set, right? 1 1 0 0 1. So it's basically this 2 power 0 2 power 1 to 0th bit. You add this, then you add whatever this corresponds to, which is this, and whatever this corresponds to, which is this. If you add these three, you get 3 power 25. No, so 3 into 25. Adding 25 times, you get this. But we don't do this because we directly have a 3 into 25 operator. That is, like, the computer can do that for you. 3 into 25. If you, yeah. But for 3 power 25, 3 multiplied by 3 25 times, 25 times, something like this, the computer doesn't do it for you. So you need to write a program for it, and you need to do it quickly. That's why we learned the binary exponentiation. Great. Now, what else is it applicable for? It's applicable for matrices. Matrices and what? Like matrices, simply matrices. 1 2 1 0. This is, let's call this A, B. What's A? B is equal to A square. Just recall what matrix multiplication is. 1 2 1 0. 1 2 1 0. It's basically 1 into 1 plus 2. 1 into 1 plus 2 into 1. It's basic matrix multiplication 2. And then 1 into 2 plus 2 into 0. It's 2. And so on. We can do it. Like, we can keep doing it for each of those things. Now, if A equals 1 2 1 0, A square equals, we can do the matrix multiplication A into A. We know how to do that. A into A. The matrix multiplication thing. 1 into 1 plus 2 into 1. Like, and 1 into 2 plus 2 into 0. So on. That's pretty simple, straightforward. We know how to multiply matrices. Okay. Got it. All right. A into A. A cube. A into A into A. Awesome. Turns out, here matrices can also be treated as numbers. Like, how different is it? Like, we just needed what multiplication meant here. And now we know how to do the multiplication, A into A. And matrix multiplication has a shit ton of uses. Has a ton of uses. I'll tell you what the uses are. Like, they're pretty cool. Like, you can calculate Fibonacci numbers. You must have heard these numbers, right? Fibonacci numbers, golden ratio, sunflower mein wo gum gum ke hota hai na uska, wo wala. Yeah, all that. You can calculate large Fibonacci numbers very quickly using matrix exponentiation. So for A power 16, how do you calculate this quickly? one way is to do, again, a into a into a, so on. As we discussed in the last video. The cooler way is to do a, then a square, then multiplying it by itself, a power 4, so on, getting a power 16. Fair. Awesome. Now a matrix to the power 25, it's done the same way you do it for a number. Again, split this into odd and even. Since 25 is odd, this is a power 12 whole square into a. Since a power 12 is even, a power 6, a power 12, a power 6 whole square, a power 6 equals a power 3 whole square, and so on. We already discussed this. Like, it is the exact same as binary exponentiation, just that instead of numbers multiplication, you're representing it by matrix multiplication. Got it? Yeah. That's it. So I shall show you the code. It's fairly straightforward. All right. So what can we see here? Yep. This is just a C++ code for matrix multiplication. I'll just show you the boilerplate here. This is just the matrix part. Matrix multiplication. You can this is fairly straightforward. Nothing of logic here. Going down. So this is the crux part. This is the identity matrix, meaning for any 2D matrix with non-zero determinant, that's needed, but that's not very necessary now. A power 0 is equal to 1, 0, 0, 1. Now you might ask why this? Because a power 0 should be such that a power 0, like in numbers, what did you see a power 0 as? Like 1, right? What is 1 like? What's so cool about 1? What's so cool about 1 is that if you multiply it with any other number, you should get that number, like x into 1 is equal to x. Got it? And an identity matrix is like a power 0 should be such that a power 3 into a power 0 should be equal to a power 0, a power 3. A matrix x into a power 0 should be equal to matrix x. And this is that matrix. For example, you can see it. The question was, why is a power 0, 1, 1, 0, 0? I'm just taking a 2D matrix or 2 by 2 matrix for now. This can be extended further too. Why is this the case? If you take any other matrix, x, y, z, w, take 1, 0, 0, 1, you get x, y, z, w, if you see it. And this is the only matrix that gives that way. Okay? That's an exercise for you. You can try it out. Like it's a tiny exercise. Fair. Now we understood what a power 0 is. Now we know what a power 0 is. We know what goes in here. This is the base case, a power 0. A power 0. Base case. This is the exact code. This is a very similar code to what we tried out in binary exponentiation. I'll show you that code. I think it's this. Yep. Check this code out. This is for a number. It's very, very similar to for a matrix as well. Like power of a, b by 2. And then if it's even multiplied by itself and return it. Otherwise, multiplied by itself. And this was the shaved off part because of taking the floor of half an odd number, like 7 by 2, 3.5. The 0.5 was cut off. That is the shaved part here. The exact same we are doing it here as well. A power n, we are taking a power n by 2. Got it? If it's even, we're multiplying by itself and returning it. If it's odd, since some part is shaved off here, an odd number by 2, if you're taking a floor of it, some part is shaved off. To make up for the shaved off, you're multiplying it by a again. It's very simple. So now we have a power of a matrix. Great. Awesome. So, yeah. Now, great. Now, let's see what transformations are. Like, it's more about what do matrices mean? So let's say we're trying to move point x comma y, transformation of this point is, say, something like x plus y, comma 2y minus x. You're doing this transformation. This is one transformation. This is P0. After one transformation, it becomes P1. Right? Like, this is just an example. After one more transformation, apply the same transformation here. That is x plus y plus 2y minus x, comma 2 into 2y minus x minus x plus y. This is called, assume that this is the second transformation. Why are we doing all this, you might ask? Like, this is just to show you what a 2D matrix is. So, yeah. Now, assume the question is, starting with x comma y, what, after performing about 100 transformations of this type, how will the new point look like? So what is a single transformation here? Manle, you started with 1 comma 2. A transformation of this point is 3 comma 2 into 2 minus 1, 3 comma 3. Then again, this, if you transform this again, you get 3 plus 3, 6 comma 2 into 3 minus 3, 3. So on. Right. What does this look like in the coordinate plane? So when you're starting at a point, say exactly, let's say 1 comma 2, you apply this transformation x plus y comma 2x minus x. That is, from 1 comma 2 you went to 3 comma 3, and then you went to 6 comma 3, and so on. You keep, the question is, the problem statement is, after 100 transformations, where will you be? Now again, one way to solve this problem is write each transformation one by one. Matlab 1 comma 2 hai, then I went to 1 plus 2 comma 4 minus 1, again some other point, 6 comma 3 you'll get, then 9 comma 0, and so on. Like 1 comma 2, then 3 comma 3, then 6 comma 3, then 9 comma 0, and so on. That will be some long process or something. If you want to calculate where it goes after 100 transformations, it's a long process, and it's not feasible, like not scalable. If you want, if the problem demands you to ask to solve this problem for like 100 or 1000, that's very slow. So how can we do it faster? Let's look at what happens here. X comma y moves to x plus y comma 2y minus x. What is happening here? This is just applying a matrix on this point. Now you might ask, what do you mean by that? That's a point. Like, what do you mean by applying a matrix on that point? I'll show you. So we write xy as a 2 by 1 matrix, x, y. Then we add the coefficients here. 1, 1, minus 1, 2. What do we get here? 1 into x plus 1 into y, x plus y, minus 1 into x plus 2 into y. That's basically 2y minus x. Right? We took what the coefficient of x is here, y is here, x is here, y is here, minus 1, 2, so on. Now, basically, what this means is if you apply this, what do you say? I think let's make this correct. 1, 1, minus 1, and 2 to x comma y, any x comma y, you'll get the transformed version, right? Awesome. Let's just look at the, I'll just read it. X comma y, 2, x plus y, 2y minus x. Matrix was 1, 1, minus 1 and 2. Y. Let's call this matrix as A. Now, you get a result here. If you apply A on this again, it's as good as applying A on this twice. Like, you get some shit here, right? You get some stuff here, right? Something you get here. You put this here, whatever this is, and you apply the matrix A again. 1, 1, minus 1, 2. And you get some result. This is like applying transformation on this and again applying a transformation on this one. Like you're applying the transformation on the already applied one. That's like applying it twice. So fun part, you can actually write this as applying it on this again is as good as A square into xy. We know that A square, you get a 2 by 2 matrix. That's basically the matrix corresponding to transforming it twice. That's a new transformation now. And the matrix for that is A square. You get a new matrix. The matrix transformed twice. Similarly, if you make it 200, you get a new, this is the point basically. This is the point here. If you apply this transformation to this point, you get a new point, single transformed point. If you apply this transformation 200 times, that's A to the power 200, you can write it as this also, like A to the power 199 into A into xy. That is, you're applying this transformation to an applied transformation. It's basically A to the power 200 into xy. Got it? So if the question asks you to transform it 1,000 times, it is as good as A power 1,000 into that point, whatever that point, applying that matrix on that point. We saw what applying a matrix on that point means. It's just matrix multiplication. Write that point as a 1 by 2 matrix, which is xy, and then you get a new point. You calculate A to the power 100, A to the power 1,000. We know how to calculate a matrix per 1,000, right? Binary exponentiation. As good as that. Matrix exponentiation, anything. You can call it anything. Up to you. You get a new point, which the new point is such that if you transform this 1,000 times with that operator itself, you will get this new point. Like if you convert x comma y to x plus y, 2y minus x. Now this new point, write it here and do this conversion again. Write it here, do this conversion again. And if you do this 1,000 times, you'll get this, the new transformed point. But you don't have to do it 1,000 times. Like when there's a smarter way, why do you want to do it 1,000 times one by one? That's boring. When you have a quicker way, you can calculate this as O of log n, right? Matrix multiplication of 2 by 2 matrix is just like a bunch of 8 steps or something. You know, right? Like you're multiplying 2 by 2 matrices. There are a constant number of operations there. A single multiplication operation of a matrix takes 8 basic operations. Correct? Like if you calculate it, it's going to be 8. 8 operations. And since you're doing a binary exponentiation with power 1,000, it's going to be log 1,000. Log 1,000 to the base 2 is about 10. 10. So you're done with 10 matrix multiplications itself. With about 10 matrix multiplications, 10 to 20, you can calculate what the 1,000th transform will look like. This x comma y, if you keep transforming one by one, where you'll reach after 1,000 places, 1,000 times after doing that transformation, the final product, you have it. Fair. Instead of doing it one by one, that's going to take O of n. This is going to be O of log n, the faster method. Awesome. So, yep. Now, moving on to linear recurrences. What's a linear recurrence? A linear recurrence, the word says. So, let's say a1 equals 1, a2 equals 3, a and so on, an equals an minus 1 plus 2an minus 2. I every time is the border, man. I need to be more careful here. Plus 2an minus 2. Great, I fit it in. Awesome. That means a3 equals an minus 1 is a2 is a2 plus 2a1. a4 equals a3 plus 2a2 and so on. Got it? Like, you can calculate this, whatever this is. 5 either you'll get 5 plus 8, 5 plus 6, 11, and so on. Like, a linear recurrence can be an equals c1 a1. I mean, it's more like it doesn't have to be a two terms. It can be a single term as well. An equals an minus 1. This is also linear recurrence, but it's not so special, right? An equals 2an minus 1. This is also a linear recurrence. Also not so special, but you know what this is, right? Say the base case. Always, a linear recurrence should always have a base case. Have one base case or more base cases depending on the recurrence. Like if there's only one term here, you suffice with one base case. A1 equals say 3. Then you can see an equals 3 into 2 to the power n minus 1. Every time 3 is being doubled. A2 is 3 into 2. A3 is 3 into 2 square. A4 is 3 into 3 into 2 cube. So on. So pattern is 3 into 2 power n minus 1. Okay. For this. But like not all your recurrences will be that simple. Sometimes you have a power n minus 2. So an minus 2. So an minus 3 plus an minus 3. That's 3, by the way, and I miss the margin again. I'll get better. So yeah, this is also a non-trivial linear. Like you can still solve it. Like it's not a big concern or something, but this is something which is not trivial to solve. Yeah. All right. Now, why am I telling this after matrix exponentiation? So let's talk about Fibonacci for a minute and we can see how it relates to matrix exponentiation. What is Fibonacci? What's a Fibonacci sequence? 1, 1, 2, 3, 5, so on. All right. So basically, Fn, it follows the recurrence. 2 is equal to 1 plus 1, 3 is equal to 2 plus 1, 5 is equal to 3 plus 2, and so on. It follows the recurrence. Fn equals Fn minus 1 plus Fn minus 2. We need two base cases here. We need to start from F3. Without the base case, recurrence is like, it doesn't say anything. You need base cases for a recurrence. You can't keep going back forever. You need two base cases because there are two variables here. The base cases are F0 equals 1, F1 equals 1, then F2 equals F0 plus F1, F3 equals F1 plus F2, and so on. Now, how do we introduce matrices into this? How do you introduce matrices into this? Okay, look at it closely now. So you have 1, 1. Let's take the matrix 1, 1, 0, 1. One second. It's equal to 1 into 1, 2, 1. You get this and then you apply the same matrix 1 1 1 0 2 1, you get 2 plus 1, you get 2. Do it again. Let's see what we get. 3 plus 2 and 3. Did you look at that? 1, 2, 2, 3, 3, 5. Okay. You can see that new Fibonacci numbers are being formed here. Can you see it? You might wonder how did he come up with the matrix? Like, that seems like out of nowhere. I'll tell you where that came from. So, what are we doing here? To calculate Fn, we need Fn minus 1 and Fn minus 2. Now, let's to Fn minus 1, Fn minus 2, let's write them here. We need these both to calculate what Fn is. Now, we need to get Fn here somehow, and we need to get Fn minus 1 here somehow, so that we can use it to calculate Fn plus 1. Similarly, we can calculate Fn plus 2 by moving this operation here, by applying this matrix again and again. You can get more Fibonacci numbers quickly. Now, how did we get this? What matrix? Like, we know that Fn is equal to Fn minus 1 plus Fn minus 2, which means 1 into Fn minus 1 plus 1 into Fn minus 2, essentially putting 1 here and 1 here. Now, how do you get Fn minus 1 here? That's just Fn minus 1, that's it, nothing special. You can directly put Fn minus 1 here. That's essentially 1 into Fn minus 1 plus 0 into Fn minus 2. 1 into Fn minus 1 plus 0 into Fn minus 2. It's very simple. Wow, you got this now. Now, on top of this, you want to apply, and on this, if you apply the same matrix again, you're going to get Fn plus Fn minus 1, Fn into 1 plus Fn minus 1 into 1. You get Fn plus 1. And here, 1 into Fn plus 0 into Fn minus 1. Fn again. That's so cool. So, what did we get here? We applied from Fn minus 1, Fn minus 2, you got Fn minus 1. And from this, if you applied this again, you got Fn plus 1. And on this, if you apply it again, you get Fn plus 2, and so on. So essentially, what we did is, like, we applied a transformation, and we discussed how the transformation came. Like, how would you come up with the transformation? And turns out you can apply this transformation on the already applied result, and you get a new transformation. That's so cool, right? Meaning, if you apply 1 1 1 0, the 0 is far. Okay, 1 1 1 0, and if you apply it to Fn minus 1, Fn minus 2, you're going to get Fn plus 1, like, though it increased by 2, Fn. And since we know that matrix multiplication is associative, that is M1 into M2 into M3, you can do this in any order. This is also equal to M1 into this, like associative. Like, you can treat them as numbers, essentially. Got it? This is essentially, if you call this A square into Fn minus 1, Fn minus 2 will give you Fn plus 1, Fn. So, let's just define a few things here. A equals 1 1 0, 1 0. A into Fn minus 1. This is just to revise, this is the nth Fibonacci number and n minus 1 Fibonacci number. This is equal to Fn plus 1 Fn. A square Fn minus 1 Fn fn minus 1 is equal to fn plus 2 fn minus fn plus 1 and so on. You can generalize it by saying a to the power k into fn minus 1, like fn minus 1 पे if you apply a power k, you'll get the n plus k. fn n minus k fn and fn minus 1 पे a power k apply किया, like if you apply a power k, multiply the small matrix by a power k, a to the power k, you'll get fn plus k and fn plus k minus 1. Got it? We saw how that came. Like if you just applied a, it increased by 1. If you applied a square, it increased by 2. If you apply a power k, it increased by k. It's as good as that. fn plus k minus 1. It might seem a lot of variables here, but just look at it once. This is very important, okay? Yeah. Awesome. But how will this help us calculate an nth, like 10 power 9th, a billionth Fibonacci number very quickly? We'll do that. What did we see here? A into f0. Like instead of n, I'm putting just what do you say? 1 and 0. Okay, f0 will give us f2, f1. Correct? A power 1, a power 2, f1, f0 will give us f3, f2, and so on. A power 100 into f1, f0 will give us 100 plus 1, 100 plus 0, 101, f100. That is so cool. We got the 100th Fibonacci number by just multiplying a power 100, multiplying this matrix with f1 and f0. Very straightforward. All right. Great. If you want, you put 10 more zeros here. You can put 10 more zeros here as well. Simple. It's very simple. Okay. Now, and what did we revise here? A power 1000 into that small whatever 1 1 1. F1 is this and f0 is this, right? F1 and f0 will give you f1001, f1000. Fair. Peace. Now, how do you calculate a to the power 1000? A square, all of them are 2 by 2 matrices, right? Like a square, a cube. We can calculate this again by binary exponentiation. We already discussed that last topic. So we can do that again. So if the matrix here is, we just discussed 1 1 1 0 now. If we take a power of 1000 to this, we'll get the new matrix. Like we'll get the new matrix, and then after we can apply this on this, and then we'll get Fibonacci directly. We'll get the nth Fibonacci number directly. This into 1 1. Here you'll get f1001 as we discussed here. Here you'll get f1000. Fair. Easy. And this we have already discussed that you can calculate it in log of 1000 to the base 2. Awesome. Great. Using this logic, you can get the nth Fibonacci number in O of log n. Awesome, right? Great. Let's look at the code. It's very straightforward, like nothing fancy or anything. So here, let me use the pen. So here, this is get the nth Fibonacci number. I'm initializing the first matrix, which was 1 1 1 0. Here 1 1 1 0. and power of fib of n. This will return, this will give me, what is the power of this matrix? Power of, this will give me, what do you say, 1110 to the power n. We already discussed previously, power of a matrix and all that stuff. How do you take power of a matrix? And I explained each bit of it, right? If you remember correctly, like just about 15 minutes back. So take the power and return the topmost element, and that will be your answer. Why? Because we know that 1110 power n into 11 will give you fn plus 1 fn, right? Meaning, let's see how this will look. Okay, meaning let's say 1110 to the power n equals a00 a10. I just name them as a b c d. We know that a plus b is equal to fn plus 1. A plus b here is equal to fn plus 1. Is equal to fn plus 1. Then c plus d is equal to fn. Got it? Awesome. Yeah, fair. A plus b equals fn plus 1, c plus d equals fn. Now, I'll just make a change in the code. You just need to return, for fn, we just need to return the sum of the bottom two elements, correct? Matlab, in the 2D matrix, we just need to return the sum of the bottom two elements. And that will give us fn, correct? Why was that the case again? Do you remember? It was because whatever this matrix power n is taken, this multiplied by 1 1, matlab idhar jo value aayega, this into this plus this into this should give you fn. Fair. That's why we are giving a plus b is equal to fn plus 1, c plus d, the bottom two elements should give you fn. Rationale being a b c d 1 1 is equal to fn plus 1. Wait, I need to erase this stuff. This is too much here. A, B, C, D. We already have this matrix, okay. Into 1, 1 will give us fn plus 1 fn. Which means C plus D is fn. C plus D is equal to fn. We don't know fn. We know C and D. So we can calculate fn very quickly. So we just need to return. We have the matrix A, right? A to the power 1000 or a to the power n, for example, just generalize it for now, power n. We get this matrix, which is a to the power n equals this. And then in that matrix, we return C plus D, which is essentially that power mat 10 plus 01. Simple. And you get the answer directly. Cool, right? Like you can get it so quickly. Like 1000th Fibonacci number. We know that a power n can be calculated in log n, where a is a matrix or a number. In this case, it's a matrix. Still, you can calculate it in log n to the base 2. By this, you can calculate like nth Fibonacci number. Like n may, after you get the matrix, you're just doing a C plus G, and that's your nth Fibonacci number. That's enough. That is like sufficient now. So in O of log n, you're calculating the nth Fibonacci number. Where previously we calculated it in, like, if you're doing it like in a brute force or a slow way, you need like one by one. It's going to take n steps. meaning 1, then 2, then 3. You need to calculate one by one. But with the matrix exponentiation method, you can calculate it in log n, O of log n. 1 by 1 would take O of n. Too slow. Nice. Fast. Cool. So do this. Great. All right. So I'm done with the class for today and lecture for today. And if you like this video, if you learned something from this video, like, do drop a like button. And if there's anything I need to incorporate inside my video, please do let me know. And there's a lot more useful content coming in this channel, so if you really want access to all that, do subscribe it. Thank you.